thank the organizers for organizing this very nice conference and for inviting me to give this talk. And so, yes, I want to speak about OCaml at LexiFi, which is where I work. LexiFi is a software editor company based in Paris. It was founded in 2000, so it's a little over 25 years now. Its software is fully written in OCaml since the beginning. So we are talking about in 2000, it was OCaml 3.0, if I'm not wrong. And basically, what it does is to, it's a company, it sells software to handle all aspects of specific kinds of financial products called derivative contracts. Its technology is based on a DSL, an algebraic DSL, that allows it to describe these contracts in a very generic way. And by doing that, it can apply kind of a programming language approach to the treatment of these contracts. And this was a very novel, and it is still today, a very novel approach in this business. And so here I just put, just to have a little bit of background, so the company, in a sense, began with this paper from 2000, from ICFP in 2000, which was written by Simon Peyton-Jones, Jean-Marc Hébert, who created LexiFi, and Julien Siward, where they describe this kind of all this the idea of using these combinators to describe this kind of financial contracts. And this is how the paper ends. So it says, well, everything we've done in this paper is very nice and good, but well, we have to do all this. We have to continue to do all these other tasks, and of course, we need to validate this in the real life, not just in a paper. And that's, in a sense, that was the beginning of LexiFi. LexiFi was created precisely to take the ideas that were discussed in this paper and try to create an actual product out of it and to sell it, of course. Back in 2000, LexiFi was probably the first company to create software in OCaml, to create and sell software written in OCaml. So at the time, it was an orthodox choice of language to build a commercial desktop application, but it turned out to be a really good choice, and I think it allowed a rather small development team to be really productive and to do more than what we could have done with more standard languages. So the other important point is that LexiFi applies OCaml to a kind of software which is outside of the traditional areas where OCaml is applied, which is more on the static analysis or high assurance software, compilation, all these kind of things. We are just building normal, in quotes, applications, normal back-end software, client-server software, web applications, all kinds of applications that typically are built using other languages, mainstream languages. And just to finish this slide with a kind of a historical note of something I learned very recently, and I was kind of surprised because it's not the first thing that came to mind. When OCaml was being considered as a choice to build, when LexiFi was created back in 2000, so 25 years ago, some of the key, some of the factors that made that tilted the scale towards OCaml, where is what's written there. It was one, the fact that you could build OCaml code with a standard build tool, make, that you could write, you had an easy FFI to interface with C libraries and through C libraries to basically anything, and that you had the OCaml compiler was small, very compact, very readable, and open source, so it was easy to modify. Even today, the compiler still has those properties, but it was even more back then. It was smaller, simpler, and easy to modify. And the fact that it was easy to modify was important for LexiFi, as we are going to see in a bit. So here I just included a few screenshots just to give you an idea, to have in mind the kind of interface that this is just like the desktop application, the kind of interface that we build using OCaml, of course, and the kind of interface that the desktop application has. This is the web version of that application, just to have something in mind of how it looks. Right. So before I continue, I just tell you a few words about myself. So I've been working at LexiFi for just over 10 years. So I have never worked, I don't have a background in computer science or had worked as a programmer before joining LexiFi. I have a background in math, and I had learned OCaml as a hobby. Joining LexiFi actually turned out to be an excellent choice for someone that is interested in OCaml, because LexiFi, as I hope to convey to you, has a very long and unique relationship with OCaml. And so through this, since I joined LexiFi, I became involved with a lot of things that have OCaml in its name. And and so in particular, I try to help maintain the OCaml compiler nowadays. And I'm also in the OCaml Foundation. So, so if you want to talk about any of these subjects or any other subjects, you are welcome to, I hope you'll come and talk to me. So now, LexiFi and OCaml. So as I was saying, LexiFi has a very unique history with regards to OCaml, and in particular, it played an active role in the development of the compiler. For example, our current CTO, Alain Frisch, that some of you may know, before joining LexiFi, spent a few years working at the Gallium team at INRIA, which is a French research institution where OCaml was born. And I say OCaml and not CAML, because CAML actually was created a bit before in a predecessor of this team. And LexiFi was also a founding member of what was called the OCaml Consortium, and nowadays the OCaml Foundation. The OCaml Consortium was the predecessor of the OCaml Foundation. And not only that, but through LexiFi, so LexiFi brought two big technology clients, namely SimCorp and Bloomberg. They are very large companies, as you know. And LexiFi brought them to the consortium and then the foundation. And this is good because they are giving money to fund and to develop the OCaml community, so that's good for everyone who likes OCaml. And also, they themselves, these companies, developed and grew, created and then expanded internal development teams that work with OCaml. And that's also very good because it means there are more jobs where you can get paid to program in OCaml. And so I said that LexiFi played an important, an active role in the development of the compiler. And so here there's just a kind of an assorted list, a quick list of things that features of the compiler where LexiFi played a role, an important role, either completely or in part. So I'm not going through each of them, but you can see that some of these features are nowadays very common features of the language and widely used. And in particular, apart from specific features, a lot of, among the people at LexiFi that participate in the development of the compiler, we have dedicated a lot of time reviewing time, so reviewing things in the compiler repository and doing bug fixes and standard library contributions. And in particular, reviewing time is something that is always in short supply in the compiler repository. So if you are looking for ways to get more involved in the development of the compiler, just trying to do a bit of review or just even to say, I tried this, it works, I tried this, it didn't work, or things like this, is incredibly useful and very valuable. And so I invite everyone who is interested to do that. So it's not just a compiler that LexiFi interacts with, so there's also a number of tools that we developed internally and that we open sourced over the years. So some of them became popular, some of them were adopted in different ways by the community, others have been forgotten. Well, for example, here I mentioned some. So FlexDLL, if you ever use OCaml on Windows, you are using FlexDLL. setLex is a Unicode Lexer generator. CSML, I'm going to come back later about it. It's a .NET/OCaml bridge, so it allows you to call .NET APIs from OCaml. And this is what we use to build the native Windows UI that you saw in the screenshot. GenJS API, it's probably one of our most popular open source releases. So it's a JavaScript generator for code that is compiled with JS of OCaml. And it is used by a number of projects, and in particular it's used to build the client side of the OCaml SP, of OCaml SP. Right. So next I want just to give you a kind of a very concrete insight into how we actually use OCaml at LexiFi. So it's not just idealized, just a description of how we actually program in LexiFi program in OCaml inside LexiFi. So this is just a little a screenshot of count of lines. So we are talking about a mid-size monorepo, so about 900,000 lines of code, 1,500 modules. So it's not small, but it's not very large. I think the other day someone told me that at Jane Street their code base is about 70 or 75 million lines of code, if I understood correctly. So we're currently running OCaml 5 in production. So the migration from OCaml 4 was straightforward, the actual migration, but of course, some of the issues that were discussed today in the SEMgrep presentation, we ran into them as well. So mostly about increased memory usage. That's an open issue that we hope will be, I mean, it's actively being worked on, and so we hope that it will, things will improve soon-ish. And also there is some performance degradation regarding everything that has to do with weak pointers. So we are particularly heavy users of weak pointers, and so maybe that's why we noticed it more. So some of that degradation was expected because of the multi-core runtime. Right. So we target Windows, of course, is our main desktop target, Linux, and the web from the same code base. And I mean, the developers, we work mostly on Windows machines with WSL, so that in a sense gives us the best of both worlds. We have a native Windows environment to run things on the Windows, and we also have a native Linux environment, I mean, 99% native Linux environment under WSL. So, of course, we have, among our developers, we have users of Emacs, VI, and VS Code, and we use LSP. So we use OCP Andent internally at LexiFi. So OCP Andent works very, very well for us. It's very easy to integrate, and it doesn't force a specific formatting style on you. So we tried OCaml format, which we agree with, the kind of the objective of OCaml format, but we had a few obstacles. In particular, we don't have a solution for what happens when, if you say you format your current master branch and then you make a bug fix that you need to cherry pick to deployment branches that are, frozen in time in the past. You cannot easily cherry pick these bug fixes because the formatting won't match. You would need to format the old branch as well, which is kind of problematic. But eventually, we would like, so that's why we haven't switched to it, but we would like to switch to it eventually. Regardless of OCaml format, we have a very strong policy of not wasting time discussing whitespace during review. And in general, whitespace diffs are strongly discouraged. A change that only changes the whitespace is strongly discouraged. And this is because it harms the ability to track a change over time. using Git. And that, the ability to do that is really critical when you are dealing with a large code base, and especially very old code base where you need to be able to track how things happen. So about the CI, so very quickly, so we tried all the standard, not all the standards, but Travis, Abeya, and GitHub Actions. We found it in our experience and in our environment not to be very efficient. Maybe because, so one reason is that they are completely stateless. And so anything you need to install, even clone the repository, it needs to be done each time you launch a CI run. And so it was taking a long time, especially on Windows. It's very inefficient. And so actually currently we have a few dedicated virtual machines that we manage and that we manage with Jenkins. And they are not, the CI is not fully stateless. So for example, we share the Git clones. We share a number of, all the packages, kind of the development packages that need to be installed. All that is shared. We don't try to do that each time we run the CI, but it really helped us to make things practical. We went from 40 minutes, on Windows, which is slower than Linux in general, we went from 40 minutes for each individual run to around 10 minutes. So it's a considerable improvement. And of course, we keep a binary cache of all our dependencies, the compiler and all our dependencies so we build the cache in the CI, we store it somewhere where we can access it, and then, so in a developer machine, we can just clone this binary cache and start developing in a matter of seconds. We don't need to, each time for example, you switch between branches and maybe your dependencies have changed or your compiler has changed, we don't need to recompile everything. So this is actually very useful for productivity. Right, so about the build system, so we had several build systems. So we started with Make, then for a long time, we had OMake. I don't know if you remember it, and now Dune. So we were actually quite happy with OMake. It worked quite well, and it was easy to extend. But at some point, it stopped being maintained and developed, and so we moved on to Dune at that time. Dune provides a pretty good experience, I think, for mostly OCaml code bases. It has a lot of built-in knowledge about OCaml, things which otherwise you have to do by hand, and sometimes it's tricky to make it work. And so we are actually quite happy about Dune. It has very good Windows support, that's also good. And we only have a few long-running gripes about Dune. So one is that Dune over-approximates the dependencies between libraries. So if you have a library A that depends on a library B, it considers that every module in A depends on every module in B, which means that if you modify any module in B, you are going to recompile all of A. And so it produces excessive recompilation. So when you are in a kind of developing iteratively, so you edit, you compile, you run, you edit, you compile. Each time you compile, this adds considerable time to your recompilation, especially on Windows, where this model of compiling by spawning many processes in parallel is not really the best situation for Windows. Windows is not optimized for this kind of approach. We actually did some independent experiments about switching to Ninja, but one obstacle, for example, is integration with Merlin, because today Merlin communicates with Dune using a kind of semi-undocumented protocol. So about libraries, so here in this slide, I think there's a lot of overlap with the presentation from Malcolm a few moments ago. Indeed, for us, we are very conservative when using libraries, because libraries mean a lot of code where, it means bugs, potential bugs, especially in code you don't know, and also security issues. And also licensing issues sometimes. The library may not be compatible with what you want to do with it. And so we have a very strong preference for very small, well-focused libraries that we can, if necessary, we can go jump into the code and, in a reasonable amount of time, understand and fix a bug inside the library if necessary. And also that we know it's not going to take control of our code base. I mean, we use it when we need it, but otherwise it kind of disappears it disappears into the background. And so just to give you an example here, I give you the full list of OCaml libraries that we currently link into our executables. And so I'm not going to read the whole list, but probably the largest library here is CAML PDF, but which is a library to read and write PDF files, but it's a very focused library. Otherwise, about half of them, they are just C bindings to C libraries. They are bindings to C libraries. So OCaml are bindings to libcurl, PostgreSQL, SQLite are bindings to, and CamelZip, they are bindings to the corresponding C libraries. CMarket is a common markdown parser, and UUTF, UUCP are Unicode libraries, and so on. One library that I mentioned because it's not very well known is OCaml D2A. It actually solved an important problem for us when you it solved an important problem. Where was I? Here. It solved an important problem for us, which is that when you convert a float to a string, OCaml typically asks the C standard library to do that, to convert the float to string. And there are differences between the C standard libraries of different operating systems. And so it can happen that the same float may be printed in different ways on different systems, and that causes a number of problems for us. So OCaml D2A actually implements a more recent and completely independent of any C standard library algorithm, and so we are guaranteed to have the same textual representation for all floats. And of course, we use also some non-OCaml libraries. So we use what's called the Intel Math Kernel Library. So it's a free closed source library of vectorized numeric operations. libXL is a library to read and write Excel files, Chromium on Windows, and then some specialized user interface widgets. So about OPAM. So we don't use OPAM. This was mostly historically because OPAM only appeared in 2011. So and then it didn't support Windows for a long time. But also, I would say, even today, even if we were creating, LexiFi today, I'm not sure we would use it because a package manager like OPAM, but other package managers have the same issues. I think they address the normal workflows of an industrial environment such as LexiFi only tangentially. I mean, you can use it for it, but it doesn't really add that much because, in our environment, like I said before, we are very conservative in how we use libraries. We typically want libraries that have very few dependencies anyway. And so having being able to install lots of libraries very easily with one command, being able to update libraries with one command like this, these are all things which are not really useful in our environment. We typically don't, reproducibility is very important for us. So we don't want to update libraries. We don't want to have to do an OPAM update and have the metadata of our libraries and in particular version constraints change our fit and all this. And yeah, the libraries we use don't have almost dependencies anyway, so the constraint solver doesn't really add anything. Right, and in terms of actually accessing the libraries, to do that, actually Dune solved it for us, because with Dune, you can just drop your library inside your repository and start using it. So that's actually the most important part for us, to be able to use libraries. About PPX, we actually almost don't use PPX. We don't use PPX actually in our compiled code, but we use PPX in these two tools. So there's Landmarks, the time profiler that we developed internally. So it uses PPX for instrumentation. So when we are doing time profiling, we are using PPX. And then Gen.js API, which I mentioned before, which is a JavaScript binding generator. It has a PPX mode as well. It has two modes. One of them is a PPX mode. But in general, we find PPX to be kind of fragile because it exposes the compiler syntax tree. And of course, if you are using PPX, you are indirectly degrading your compilation time because every file I mean, you need to preprocess your files. Yes, also, I mean, this might be kind of a niche complaint, but you know, once you are using PPX, it's harder to just compile a file, right? You need to do something else. You can't just have one command line that you can play and to debug or whatever by hand. And the last reason is that actually the one really useful PPX, which I think is one of the main applications of the PPX infrastructure, is PPX deriving, that allows you to derive objects from type definitions. But that problem we solve in a completely different way. So it's what we call runtime types, and I'm going to come back to this. So let me just now skip that. I'll skip a few slides in order to have a few minutes at the end for questions. So so language use. So here I want to just explain a little bit how we use the language. So we are heavy users of advanced quote-unquote features of the language. This means not really advanced, but features which are sometimes considered to be a bit outside of the core of OCaml. So we use a lot. We use objects quite a bit to implement mixins and actually the .NET bindings that I spoke before through CSML. We use quite a bit of GADTs when manipulating these runtime types. We're going to get to that. And first-class modules, type disambiguation. We use it everywhere, inline records, and so on. So in general, regardless of that, whenever you are in a doubt between using some fancy types to enforce some invariant or just using normal types, and we think that one should avoid fancy types. It just makes the code harder to read and harder to modify. And of course, we try to use optional result types and library boundaries and using exceptions just inside implementation. But well, we have a lot of legacy code that still uses exceptions to report errors across boundary types. And yeah, of course, we try to use immutability when possible, but we have a lot of imperative code. OCaml is a great language to write imperative code in anyway. Readability is very important. So actually, anything that harms readability is a bad idea, in my opinion. And so in particular, infix operators other than the arithmetic operations I think are a bad idea, and monadic operators and monads, mixing monads and these kind of things don't work so well in my experience, long term. So for debugging, of course, the lack of a debugger or native debugger, it's a common complaint. We use printf debugging. We have always used printf debugging. At this point, I've used printf debugging for so long that I can't even think about debugging any other way. But all right. And definitely one point is that printing arbitrary values is very useful. It's actually one of the key, the fact that you can write print x in Python and just have x in your terminal is one of the main differences, I would say, in terms of how you feel about the language. And this doesn't exist in the official OCaml, but we have it inside LexiFi using these runtime types. So we are happy in that sense. So a little bit about, we also about kind of more numerical stuff. So at LexiFi, because we are dealing with contracts, and at some point we have to price those contracts. We have to get numbers out of those contracts. And so for that, we need numerical code. And so we write it also in OCaml. So as you know, floating point numbers are boxed in OCaml. So this typically is a source of inefficiency. But the native code compiler is actually quite good at avoiding the boxing for intermediate results if you write your code in Fortran, what one could call Fortran style, which means no recursive function at all, just loops. And actually for numerical code, using loops is often much clearer than using recursive functions. What else? Yeah, we use the no flat float array mode. It's not very well, not very well known. So it means that float space array is always boxed, like the usual mode where float space array is unboxed. The downside of having it being unboxed is that every array operation has a dynamic check that has to happen to know if you are in the unboxed or in the boxed case. So by disabling this mode, all array operations become a little bit more efficient. And then if you really want an unboxed float array, you have to use the float array type, the dedicated float array type. We don't know how to use f lambda either. So the reason is that the performance critical part of our code is very, it's a small subset, and that subset is hand-tuned. So we use special data structures, special code, we optimize it by hand. At that point, f lambda is not going to bring that much to us, to the table. And for the rest of the code is not really performance critical, and so optimizing the rest of the code is not necessarily, it doesn't really do that much for us. And it does have a few downsides for us. So if you use f lambda, you get bigger artifacts and increased compilation time, and also the gap between the source code and the generated code becomes larger. And if you, for example, if you are used to examining the generated assembly code, it's nice that it corresponds to the source code. The more inlining you do, the harder it becomes to read that assembly code. And we handwrite our C bindings. So at this point, I'm just going to quickly, so I'm just going to stop here in this slide. So this was CSML that I mentioned before. So just to give you a taste of what it is. So basically CSML is, so you see the stuff on the top left of the screen. So it's a kind of, it looks like you're the definition of an OCaml class, but it's a bit different because you have class T equals system Windows forms control. And so you basically, there's this DSL that you use to describe an OCaml interface using classes and the corresponding .NET components that it has to map to. And CSML takes that DSL and it generates OCaml code and C# code. So the generated C# code is, for example, the thing on the top right. So that when you call the OCaml class that is generated, it will communicate through using the FFI with .NET and call the generated C# code. And the C# code will take the arguments, the OCaml arguments that you passed as arguments, which are basically pointers into the heap, and convert that structure into C# values, .NET values, pass it to the .NET target, whatever the method or the function you're calling, take the result, which is the .NET value, convert it back into an OCaml value, and send it back to the OCaml side, right? And so that's CSML, and that's what we use to build the native UI on Windows. So now let me just, this is just the installer. So here in these slides, I just talk a little bit about how we deploy the software on Windows, but let me just skip all this to come to this section, because otherwise we won't have time. So it's what I call the secret sauce, and this is what I mentioned before. So LexiFi maintains a fork of the compiler, so 25-year fork, and so it is extended with a kind of type reflection. This means that we can manipulate types at runtime, and it's actually key, this extension is actually key to allowing us to be as productive as we are. And so just in this screenshot, I hope to give you the main idea of what it is. So on top, you have this function show. So this function show takes two arguments, one label argument called T. The type of that argument is T type. And the second argument of this type T is a polymorphic function, can be anything. And you can see that what we do in the function is a kind of pattern matching on the first argument. And the first argument is a sum type, where you have one case for each type of OCaml, if you want, or some subset at least. So you have the case of int, the case of string, and it's a kind of GADT you can make out, because in the first case, int x, which is the second argument, is known to be an int, so you can call print int on it. In the second case, string x is a string, so you can call printf on it, and so on, right? And so this you can do today in normal OCaml. You could write such a function. You could define such a sum type. There's nothing magical about it. But let's look at how it is how you can use it. And so this is specific to our compiler. You see below, I launched the top level, and so when I load this file into the top level, and so I have a function show with the 2 arguments. I define a variable x, which is a triple, 42, consisting of a first component an integer, second component string, and third component is a list of floats. And then I call show, and I pass the variable, and it prints the variable, the value of the variable to standard output, right? So that's what the code does for us. And so when looking at that, it looks a little bit funny because we are calling show with only 1 argument, right? But the definition of show had 2 arguments. But the first argument, which describes the type of the argument, is not given at the call site, and it's actually synthesized by the compiler. So the compiler, which has type checks the program, it knows what the type of x is, and it inserts the missing argument with a description of that type. And so in the body of the function, you have access to the type of the argument. And so this is all it is, but it makes a huge, huge difference. So it means that I'll come back to the next slide in a second. You can just write a normal, we are not writing a PPX here, this is a normal OCaml code where you can just write a normal OCaml function and do things as a based on the type of the argument, right? So that's the main point. And just to finish, here we don't just use that to print values on the console, even though that is an important use. Here we have at the bottom left, you can see a small type definition, a record type, right? And what you can see on the top is how some user interface that has been derived from that type. So you have the record with five fields, and you have the form, the UI form in native Windows UI that corresponds exactly to that type, and it's completely derived by one function, just like show before, right? It takes the type, it pattern matches on the different types, and it generates that UI. It generates all the getter, the setter, everything that you need to work with the UI is automatically derived from the type definition. And then on the left, I don't know if it's very clear in the projection, but it's the same UI, but on the web, right? So you see, we generate all these things automatically from the type definition. We don't do it by hand. And on the bottom right, you have a kind of XML representation of a value of that type, and the XML schema is also derived from the type definition. So you see, it's a really powerful approach. You could do this maybe with PPX, but you would need to define a whole PPX for each application, where in our case, we just define one function in OCaml to do each of these things. And so I'll finish with this. So the T argument, the first argument is synthesized by the compiler, and you can use it for all kinds of things. It's a very powerful approach, and it makes it very ergonomic, right? The fact that you then call the function and the compiler inserts the missing argument. And if you want to learn more about it, so tomorrow we have a workshop, and I'm going to try to show you how to actually implement this in the compiler, starting from scratch in less than 100 lines of code. So I hope you will all come and we'll learn that together. And now suddenly it's happening, but okay. And with this, I finish. So I just, this is my last slide. Yes, OCaml is a great language, so it's not just for static analysis and compilers, and so it's just a pleasure to work with. And with that, I don't have any. Yes, sorry. Thanks for listening. And if you are interested in finding out LexiFi, don't hesitate. We are always open to spontaneous applications.
Great. Thanks, Nicolás, for walking us through your day-to-day job. That was actually interesting. So do you have any questions?
How does the runtime type and show and all that handle type variables?
It doesn't. So you have to decide what you want to do. So if you come to tomorrow's workshop, we're going to discuss this point. But in our extension, we only represent closed types. So type variables we don't represent. I mean, representing for the type of things we want to use it for, representing type variables would not really bring much to us. I mean, we would know that something is a type variable. I mean, we don't know the type it has. We wouldn't be able to do anything with it. So basically, we can, if you try to obtain the runtime type of something that is, you're in some polymorphic context and you don't know what the type of your value is, you just don't know. You get a compilation time error.
That seems reasonable.
Great presentation, Nico. Aside from the closed types or abstract types that you don't support, what are all the differences between this runtime reflection and, I don't know, let's say modular implicits or other solutions from this dynamism from, like, not currently implemented language features, but future wishes that you might have or everybody might have?
Yeah, yes. So thanks for the very interesting question. So actually, often I hear people telling me, but this and this what modular implicit is supposed to solve. And I don't know anything about modular implicits, but as far as I know, modular implicits will help you, for example, if you know something about T1 and something about T2, it will maybe do something about T1 cross T2. But if you have a sum type or a record type, modular implicit will not do anything for you. It's just a new type that you have defined, and modular implicits doesn't bring anything to the table here. I think modular implicits and this kind of deriving mechanisms are kind of orthogonal to a large extent. And in fact, modular implicits, I mean, if you think in terms of Haskell, which I don't know much about either, but in Haskell, modular, you have type classes and then you have the deriving mechanism, and these are two different mechanisms. And I think it more or less matches the distinction between modular implicits and runtime types or any other equivalent mechanism.
Okay, great. If you have any more questions, please ask Nicolás in your spare time, because we have 10 minutes over. So yeah, one more round of applause for Nicolás for his amazing talk.
Thank you.